First of all, thank you for coming. Thank you for staying through the second day. Honestly, it's like amazing to see like the huge room, all you here. Because I still remember that scrappy, tiny startup with like maybe a dozen people that I joined. I took a plunge from my otherwise comfortable job at big tech to join this startup because I saw this massive potential to help developers, us all, to build better systems. And now I see the even bigger potential with all this. That's a little bit scary how far it goes. Yeah, this is me. So our business model of Temporal, the company, is very simple. We have open source Temporal server. You can use it for as much as you want, as long as you want, run in any kind of configuration, use different backends and databases, fine. We expect you to come to our Temporal Cloud when you decide that now you want us to run your workloads. It can be because it's more economical, because of economy and scale. It can be because you want a better reliability and want to sleep at night instead of kind of getting paged. Or it could be because you want to scale and now you're not comfortable running your own Temporal, your own system, your own service that is critical to your business at that scale. And in Temporal, we have this sort of implicit value of transparency. You'll be amazed, like Temporal employees have access to all board updates, to a bunch of documents that otherwise would be sensitive in other companies. They consider, oh, no, should be restricted access. We see pretty much everything, except for maybe some HR stuff. And so in that spirit of transparency, you want to share how we do things, how we run Temporal Cloud. Maybe sometimes we even overshare, but I'm totally fine with that. I like that. Because at the end of the day, when, and I hope it's when, not if, you decide to come to Temporal Cloud, you want to make an informed decision that you know what you get into, you know what we do there. And so this talk is sort of a continuation of a talk I gave at last year's replay, because there's some more stuff that was not there. I hope you find it interesting. When you come to Temporal Cloud, what you get as a unit of product is a namespace. Like API-wise, behavior-wise, it's the same as namespace in an open source Temporal Cloud. The difference, though, is that it's a virtual resource. Like if you run your own cluster and you create namespace and your load grows, at some point you need to scale up your cluster, and then maybe you run into the fact that you chose your shard count like 2 years ago without thinking about that. So virtual namespace is not tied to any physical cluster. It kind of lives in the ether and scales with your workload to as much as you need. But of course, there is no magic in software, right? So at any point, this virtual namespace runs on some resource, physical resource, in a data plane. And we call this cluster cells. And this is like a very simplified picture of what we run, but it covers the most important pieces. This is the AWS example, but others are similar. So for each cell, we create its own AWS account. We create the VPC, we create the EKS cluster. And that's all for isolation, so that whatever runs in the cell doesn't impact and doesn't get impacted by things running in other cells. And Temporal Server, of course, is the most important, the most critical piece of component. That's why you come to it. But besides this Temporal cluster, all the services like history matching, the front end, there are infrastructure components that run there for managing traffic, for managing security and things like that. There are a couple of databases, the main database and Elasticsearch database. And we also added a couple of years ago the write-ahead log for performance, for reliability in between Temporal and database. So it's a pretty significant machinery, but it's all encapsulated this notion of a cell. And we call it a cell because we follow the Cellular architecture, which is a standard pattern in the industry, which has essentially two rules. They're sort of the same rule. So you want to limit a blast radius of any change, and you want to share nothing. So if something happens to one of the cells, it impacts traffic, like maybe it's degradation of latency, only for workloads that go to that cell. It doesn't impact all other cells. So it's a very simple process. And it doesn't have to be a physical issue. It can be just somebody pushing bad configuration. And we know in our industry, a large percentage of outages is actually called by humans pushing wrong configuration. And if you do it fleet-wise, you problem. So we kind of follow standard business, standard best practices in the industry. So cells are deployed in the regions of cloud providers. In AWS, if I remember, I have 13 or 14 regions. You have private connectivity for private link there. You can connect through internet, all the standard stuff. As you know, we added support for GCP. And so essentially we went multi-cloud. And next year we plan to add Azure, which is my favorite cloud because nobody knows how to pronounce it properly. Is it Azure or Azure? I say Azure. And so going multi-cloud was not particularly difficult because, of course, we planned from the beginning, architecturally, design-wise, there will be multi-cloud. So we anticipated that. But still, we had to work out some differences between them, some differences in API and behavior. Like, for example, S3 and GCS, they're API compatible, but the performance characteristics are partitioning is different. IAM models are different, or the very simple fact that AWS has a managed offering of Elasticsearch, and GCP just doesn't. So we had to solve this problem. But otherwise, it's like private link, private connect, very similar. We run a single control plane that manages both clouds. For simplicity, for consistency, it's easy to manage. We anticipated in the future we'll probably push some of the components to specific to cloud provider, maybe even to region. We haven't seen a need for that yet, but we'll see. At some point, I think it's inevitable. And I kind of like this picture. I don't know, maybe because my son is a private pilot now, or maybe because this kind of physical gauges, they're kind of cooler than your traditional dashboard like in Grafana you see. And so the data plane, its responsibility is one, its sole responsibility is to just handle traffic that comes into the system. And when a process requests, send responses with high enough throughput, I can satisfy all the requests with lowest possible latency and highest possible availability. So it's kind of very challenging to get it, but it's also very narrowly focused. Control plane, on the other hand, is not on the hot path of processing requests. It doesn't participate in processing payment transactions or whatnot, but has a laundry list of other responsibilities where it needs to do. So when you configure, when you create namespaces, when you manage access, where you update your settings like certificates. And so this is a 30,000-foot view, no pun intended, of what control plane looks like. It's essentially two temporal cloud namespaces. One is control plane namespace, and the other one is infra plane. We split them in such a way that infra plane handles lower level operations, like invocations of temporal of cloud provider APIs like AWS, GCP, invoking EKS, Kubernetes clusters. And it's also managed by a different team that focuses on that. And control plane handles all the high-level operations and has a control plane database where all the cells, the namespace is used, all the settings are listed, and it does all the operations. There are a bunch of workloads that run there. So like if you don't have to squint hard enough to see that it's essentially two microservices, and they have front end, they have API gateways. In control plane cases, exposed externally. So when you use Temporal Cloud UI, the API calls from the browser go through this gateway. Same for CLI, if you manage it through CLI. Infra plane is not exposed externally. It's only for control plane to call it or some internal tools to call it. And so like, if you look at it, it's very similar to the picture you saw yesterday in the keynote and Nexus presentations. Two teams, team A and team B, want to invoke APIs. The exact same picture, and that's why we plan to move to Nexus from this and eliminate the need for this API gateway. Now, inside the control plane namespace, we use this pattern where every request that comes through an API gateway starts a request workflow. And its purpose only to maintain this context that there was a request with these arguments, and if it completes successfully, what was the result? If it failed, what was the error? So that you don't have to rely on maintaining your connection. You don't lose your context. You can always query. You can always check what happened. You have history of invocation. It doesn't do anything else. It starts the actual workflow that does operation, whatever it is, like creating new namespace or maybe updating settings. And so the bunch of these workflows run in parallel because they scale. Like there is no problem here. And some of them at some point invoke entity workflows. Think of them as kind of digital twins that are one-to-one to physical and virtual resources. There's entity workflow for each cell, there's entity workflow for each namespace, for each user, and for a bunch of other entities. And that leverages this strong guarantee of temporal server that each one of them only exists in a single instance. And so that gives us this serialization of requests and eliminates any potential concurrency because you don't want to have two updates to be happening to the same namespace or the same cell. And just to be clear here, it was not an ideological decision. It was not an executive mandate, thou shalt use temporal. No, it's just because durable execution is the best pattern we're aware of for building control planes, and which is sort of supported by a bunch of customers on Temporal Cloud now using temporal to build control planes for hosting their like database products. So it's a very pragmatic decision because we believe that's the best tool. We don't know about better tool. And temporal is the best implementation of durable execution that we know of. So what can go wrong in production service? What is the biggest threat to a production service? I would argue it's a change. So if services were static, life would be much easier. And that's sort of the benefit of mainframe, that you have the static things that stay there forever. There are rarely people change a tiny bit of code, maybe like for, I remember year 2000 panic. But other than that, it's just nothing happens. So it's very reliable when you don't change it. We cannot live in that environment. We have to roll out changes constantly, right? That's the nature of our business we're all in. And so for that, we use the standard pattern that the industry knows is rolling upgrades. We organized, grouped cells into deployment rings. They number from 0, I think today we have through 6, and then there's the ring 100. And so ring 0 is pre-production. We don't put any customer traffic there, but we constantly run our own internal synthetic load to make sure that we have loaded enough cells in that ring. And then we organize them in such a way, these rings, so that lower priority namespaces go to lower rings, and high priority workloads go to higher rings. That can be size, they can be like criticality of like payment processing versus somebody organizing CI/CD. And so when we start rolling update, as you expect, we go ring 0 first, and then when that succeeds, we go up and up and up until we upgrade all the rings. Sort of makes sense, right? This is all managed by a rollout workflow, which is started, as I explained, by a request workflow. The rollout workflow goes to control plane database, loads a list of cells, settings for rings, batches, and builds essential rollout plan. And it posts it in Slack for approval, and then it keeps updating, and it just does that and invokes one cell at a time, say, hey, now it's your turn to upgrade, in this example, temporal to the new version. And that workflow goes and does it service by service. So it upgrades front end, then matching, then history in between, and keeps checking our internal canary traffic that runs in every cell to see, okay, is there any alert? Is there any failure of canary after upgraded matching service? And if something happens, it just stops, and we can pause and investigate is it related or not. So this is all automated, and of course, workflows are the best tool for that. We use different rollout modes. In normal rollout mode, we spend 7 days in ring 0. This is, like I said, is non-production. We spend the 7 days there because some bugs may manifest statistically, probabilistically, and if there is a resource leak, it takes time for it to manifest. And then we start going into other rings, and then we slow down at the higher rings to go slower. But this is for like a normal upgrade. If we have a small patch, there's like one commit, one fix, we think risk is low, we can go expedited mode where we don't spend like 2 weeks rolling out. Like a normal mode, we can do much faster. And then we have emergency for kind of we identify the problem that may happen. And again, we understand and we think risk is worth taking, we can do it. And I think we use it maybe a couple of times if my memory serves right. And also we have all bets are off, break glass mode. I don't think we ever use it, but it's there for just in case. So we use it for upgrading temporal itself, upgrading a bunch of other components. Configuration I mentioned is a big threat if you just allow it to globally change. One example also which may not be obvious is alerts. Right? We have a few hundred alerts where essentially a threshold for our SLO. If persistence latency request P95 goes over a certain threshold, set an alert, which will page somebody on the admin's team, and then people will go and check what's going on there. And so imagine I want to change this threshold, and if I were to make a mistake and set it to whatever 0 or some high value and blast it across the whole fleet, that would potentially silence this alert for the whole fleet. We don't want to do that, and so we do it in the same kind of stage manner like we do code upgrades. So we reuse the same workflow, the same rollout workflow, just different modules. So I've talked about the rollout, but what do we roll out? And kind of how we create bits is actually as important maybe even more important than Rollout in a way. And we recently changed how we produce bits for the cloud. So this is what we've been doing up until maybe 8 months ago. We would have an open source release, like in this example, I think it's 121.0, and I would merge into internal cloud repo, where we also add things like cloud-specific stack authorization, write-ahead lock, and other components that are specific for the cloud. We'll produce a build and start going through testing, finish testing, then start deploying to the cloud. And that's kind of best practice, right? You take dependency on official releases from a dependency. In this case, dependency is our own, but that's kind of what most people do. And everything is fine except for our customers don't like frequent open source releases, like the minor release. Patches are fine, but because minor, you have to apply each one, they don't want to do it every month. They don't want to do it every week. And so we settle on sort of compromise that works best and about a quarter cadence of that. Every quarter we have a new minor release. But this is so many changes. If we release every quarter, there's a lot of changes go into the cloud, and there's so much more opportunity if something go wrong and some regression and degradation. So there are downsides to this process. Some are obvious, some are less obvious, because open source release is there before we have it in the cloud. So we switched to this process, where instead of waiting for the next minor release, we cut. Every 2 weeks, we tag a commit in open source tree, say, okay, this is a new biweekly release. We merge it, we go through the process, we start deploying it, and because we cut changes into these biweekly chunks, we essentially reduce the risk proportionally. If something goes wrong and is questionable, there is a much smaller set of changes that you can look at. There's much more reason, and we can figure it out much faster. So it's less likely to go wrong. And so we do all these biweekly chunks, and then at some point we mark the commit in open source. We're ready for this open source release. But by that point, this bit's already deployed in the cloud and been tested and run for weeks or months maybe. And so that has a number of benefits. We increased quality of process bits that go into the cloud because we test them in the smaller chunks. We increase quality of open source builds because we cut them only when we already deployed them and been running in the cloud. But also the issue we were facing, our customers would see, oh, there's open source release with this new feature, and they would ask, when will I have it in the cloud? And we would we should watch it in a few weeks probably, because we haven't tested it, we just merged it. And if we find an issue, we may need to go back. And in one release, we had 4 patches before we could push it into the cloud. Now the answer is very simple. When it's open source release, it's already there. You can use it day one. And this is all these tags, they're visible. If somebody wants to upgrade their open source, the self-hosted cluster every 2 weeks, they're more than welcome. Nothing is hidden here. Another topic we rarely talk about is namespace migration. You probably have heard of it, but we never really explain how to do that. It's very critical because of this virtual nature of namespaces. We need to move around. So I wanted to shed some light on it. You probably noticed that on the previous slides, all cells look uniform. They're all kind of the same size and shape. In reality, that's not true, because we scale up different components as we need. For example, we may need to add capacity to database for space reasons or throughput reasons. We may need to add compute if our pods are running hot, or we scale write-ahead lock separately based on the characteristic of that. So in reality, you have this kind of fleet of cells of different shapes and sizes. And so when the namespace traffic grows, we might want to move it from one cell to a larger cell, for example, or just rebalance to have a better balance of load. So this is how it works. So we want to move this namespace XYZ from cell A, where it lives, to cell B. So first we create a standby replica of it on the target cell. And then we start sending all the all tasks and all workflows to replicate it. The high priority is for recent traffic, for live traffic. And then with low priority, we also send workflows that get closed. They completed a while ago, and the retention can be different, right? And so we start moving all of this to this standby. And at some point, we catch up. All completed workflows are already there, and all currently running workflows, they get replicated maybe a few tens of milliseconds behind, or something like that. So when we're ready, we just switch primary and secondary and reverse the replication to the opposite direction and switch traffic from cell A to cell B. But as you know, network connection cannot be switched instantaneously. Some clients may be connected to cell A still, and for that we always actually forward from standby to primary so that we can process all this requests. So all traffic is processed on the primary. And then when the traffic disappears from old primary, now standby, we can disconnect, we can stop replicating, and now it's gone. And as you can imagine, there is a workflow that orchestrates that, because this process may take minutes, it may take hours, it may take days. Things they may see some errors, they may need to retry. So all of that is handled naturally by workflow. A major feature we launched this year is a multi-regional namespace. With that, we could declare that we have 4 nines availability, because now we run for you hot standby replica in the different regions. So if something goes wrong, whether it's infrastructure, connectivity, you can fail over to standby namespace. We were kind of very conservative with saying how many nines we support. We were, for a single region, not going to say more than 3 nines. You see some other SaaS vendors, they claim 4 or 5 nines in a single region. We don't play these games. It's not true. If you look at the diagram, how it looks with multi-region namespace, you see a lot of similarity with what I just showed you with migration. And that's for the reason that the same replication stack is used for both. So essentially, instead of temporarily connecting them and replicating all the traffic for the namespace, here we continuously replicate. So initially, we catch up, like when we call it namespace is globalized. We kind of do essentially migration, move everything, and then after that, it's moving all live traffic to it. And so, in addition, there are 2 the region-specific endpoints, which allows customers to run with different sets of workers in 2 different regions. Oftentimes, they have regional dependencies. They can't just have workers in one region and connect across region. They want to have these 2 sets of dependencies and then fail over if something goes wrong. So if there's any degradation in primary, we just switch primary and secondary, start replicating and switch direction of forwarding and switch traffic the same way like we do with migration. And of course, there's a workflow that handles all of that. So failover can be triggered automatically when the system detects that there's degradation and the criteria it meets to switch to failover to standby. But it can also be triggered by a human, by our operator, our on-call engineer saying, well, I don't like what's going on here, let's failover. And there's like one command to failover all multi-region namespaces from a cell to their standbys. But it can also be triggered by a customer when they see, I want to, for example, test that my system will work or whatever reason. So the question is, if we need to move, let's say, primary replica, migrate to a different cell, what happens here? Well, if you combine these first 2 diagrams, you'll see that we create another standby replica in the same region, the cell can see, in my case, and start replicating. I think it's called 3-way replication. I don't know why 3 is 2 direction, whatever. 2-way, 3-way replication. So from the primary, we replicate to both standbys. And then when the replication is done, we switch primary and secondary in the original region and start replicating from now a new primary. And again, we monitor traffic to original cell, and if this traffic stops, we can stop replicating and we can delete the secondary. Now there's a new primary, a new cell. So it's a kind of combination of these 2 patterns. And yeah, the same thing, there's a workflow that does all of that and automates and does the Slack notification. Sometimes they need approval, sometimes just post status. There is like web interface for that internally to see what's going on. So if I kind of circle back all the way from where I started, I started with saying that our business model is very simple. Open source, use it for as long as you need. No shenanigans with kind of licenses per core or any kind of crippling. No, we didn't need that because we want more developers to use the software. We want everyone. When I joined the company, when I kind of understood the whole like magnitude of opportunity, I started saying that 80% of software can be written this way. And I was kind of saying, maybe it's an exaggeration, maybe it's 70, but now I'm not sure. It could be an overstatement, it could be understatement. Because I think you're all here because you see how durable execution kind of liberates us for writing much better systems, much easier, and have more fun doing it. And so I often say, we're just getting started. And it's not a figure of speech. I think the more we do this, the more opportunity we see of what may happen. Like this conversation about Nexus, I remember I was having with Maxim before he decided to join. He was explaining to me how, we can annotate gRPC contracts and then make it standard to make it kind of completely any system talking to any system. Now we just rolled out. And that's just the beginning of Nexus story, which is a part of the whole temporal story. So I truly believe we're just getting started and we're kind of on this very interesting ride into the future. Nobody knows what the future holds. But I want to thank you for kind of joining us on this ride, being part of this kind of movement, moving in this direction. And that's what makes it all enjoyable. I covered just kind of few aspects. Of course, I don't have time to talk more about how the cloud works. But in the spirit of transparency, catch me in the hallway, catch me virtual later. Always happy to talk about, always happy to explain what we do, how we do it, why we do it this way. So thank you very much.